let's look at the ideal gas law experiment. This is the reaction that we're using. We are reacting magnesium with excess hydrochloric acid, and we are collecting the hydrogen gas. Now the setup is using this tube that is a Untitled. It captures the gas, and also it gives us the volume of the gas. And this is set up kind of funny. You set it up with the hydrochloric acid at one end, and then you put some extra water in there, and then you flip it around. And when you flip it around and you put it into this container of water, you need to make sure that there's no air bubbles in here, because at the end we want all of the volume of gas that's in here to be from the hydrogen. Otherwise the volume will appear too high, and that could throw off our calculations. So anyway, once you invert this, the hydrochloric acid that's in there reacts with this piece of magnesium that's down here, and then the bubbles that are formed will go up in the tube. As it reacts, it basically bubbles, the gas bubbles up through here, and it pushes out the extra liquid. So the gas that is up here is actually, it is our product, hydrogen, but it is actually going to also include water. Okay, and the reason that it includes water is because there's a lot of water here. This is a solution of hydrochloric acid, but there's a lot of water, and as the bubbles pass through the water, they get saturated with water vapor. And so unfortunately the stuff that we collect is not just hydrogen gas, so we'll have to take that into account. But I can tell you that the pressure of that mixture, the total pressure, is equal to the atmospheric pressure. And the atmospheric pressure is given in your data. So let me tell you a little bit about how you're going to get the pressure that you need. Remember Dalton's law. Okay, so the one that we need is this one. We need the pressure of just the hydrogen, the partial pressure of hydrogen. And as I said, this one will be in the data. The atmospheric pressure is your total. And by the way, it's in torr, which is a different unit. Torr is the same thing, or it is the same thing as millimeters of mercury as far as converting to atmospheres. So let's just note that over here, that if you have pressure in torr, you divide by 760 to get to pressure in atmospheres. Okay, but the problem is we need to also know this one in order to get to the one we want, and this one is the vapor pressure of water. And the vapor pressure of water varies with temperature. And so you'll have to look in your experiment, your data for temperature. It is the temperature of the gas that you gather, and it's the same as the water. And so the temperature of this is at that same temperature. And how do you get the vapor pressure? You know, if your temperature is 22 degrees, how do you know what the vapor pressure is at 22 degrees? Well, look in your lab manual, your experiment PDF, there's a chart. And so you'll look at your temperature that's in your data, and you'll read off a vapor pressure, and that's what you put in there. This one is in your data, and so you'll basically end up subtracting to get to your pressure that you need, the pressure of just the hydrogen. Okay, also in your data from this Untitled, you will get the volume of gas in your data. And remember, the volume for the mixture is the same for either gas, so there's nothing to do with that. The volume and the temperature of the mixture versus the hydrogen you're interested in, those are the same. It's only the pressure that's different for the two. Okay, let's look at an example. And so I only need 4 pieces of data to do this. And on my example, I'm not using magnesium, I'm using beryllium. But it works the same way. So I'm going to be given the mass of the metal that I'm reacting, the volume of gas that's produced. I will need to know or be given the temperature, and this will be the temperature for everything, the gas and the water and the water vapor. And then I'll also be given the barometric pressure, and it will be in torr, so I'll need to watch for that. So the first thing I'm going to do is I need to get everything in the right units kind of as I go. Volume will be in milliliters. I can convert to liters. That's pretty simple. Temperature will be in Celsius. And so I'm going to add 273.15 to get it to Kelvin. And I did keep track of my sig figs, but as you do this experiment, keep lots of digits. And I checked, and when I entered a whole lot of digits on the computer, it did not count them wrong if I kept those extra digits, as long as I round off at the end. So keep a lot of digits in there or you won't end up with an answer. So next I need to figure out my moles of gas. And this is basically stoichiometry, because we know how many grams of this metal we used. We can predict how many moles of hydrogen were made. And we don't have to go to grams, because what we're really looking for is N. In the ideal gas law, P equals nRT, we need that N. And so anyway, just stoichiometry. This, of course, was my molar mass. For my metal is beryllium, so yours will be different there. And this part right here, this is from the coefficients. And my coefficients were both 1. So 1 beryllium per 1 hydrogen. And then I got my number of moles. Now, mine just has 2 sig figs here. And so then I know at the very end, my answer will just have 2 sig figs. But I'm keeping a lot of digits in there so it doesn't get rounded off as I go through all these steps. Okay, pressure is the tricky one. I do want it in atmospheres, but I've got to work to get, I want just the pressure of the hydrogen, the partial pressure of hydrogen. And as I said earlier, you're going to have to use Dalton's law here. This one is the atmospheric pressure, and I write that it's actually in torr, but it is the atmospheric pressure you would measure on a barometer. Okay, and this one again is the vapor pressure of water, and you look that up in your lab manual. And so I plugged those in. This is what I looked up. Notice that this is in torr, and that's how it comes on the lab manual. And this one in your data, this is the barometric pressure from your data. It is in torr, which is good because when you subtract those, they have to be in the same unit. So then I get my pressure due to hydrogen only, and it is in torr. So I need to convert it to atmospheres. And so just like I said, we divide by 760. A torr is by definition 1/760th of an atmosphere. So anyway, I'm keeping track of my sig figs, keeping extra digits. Okay, and so now I have all the numbers that I need in the right units to put them into the ideal gas law. And so notice that when I use this, I'm using this for just hydrogen. That's why we had to get our pressure for just hydrogen, because we only have the moles of the hydrogen from the stoichiometry. So basically I'm just rearranging this to get an equation to solve for the ideal gas constant. And I plug all of that in, and I get a number. Again, keep lots of digits. Don't round yet, or when you go to calculate your error, it may be too rounded off to be recognized. So we recognize that here that it has only 2 sig figs. Okay, and then we know that's 0.08206. So it's not, mine's not that close, but that's what it is. Okay, and then to get the percent error, you're going to use your experimental minus accepted. And so this is the one from your math. And this one is the 0.0826. Okay, and then you're divided by the accepted. Oh, and then times 100 here. Okay, and this is why you need all those digits. If you'd rounded it here, then it would have really gotten off here. But anyway, so we do that. And I didn't actually show it here, but right here is where we figure out our sig figs for our answer. And then I round it off at the very end. Notice that when you take this part, these bars are that you're taking the absolute value of those. So if it's negative, like mine would be, you take the absolute zero, so the absolute value, so that it is a positive percent error.